Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Today we will start chapter number 2, probability. From this chapter, we are turning ourselves towards learning about second kind of statistics, that is, inferential statistics. Statistical inference is an art of making decisions in uncertain situations. The whole art of statistical inference is based on two concepts. One is probability theory and the other is sampling theory. In this chapter, we are going to discuss the concept of probability theory. The word probability or chance is not new for any one of us. It is used in our day-to-day conversations by coming across following statements that depend on probability for their answers. For example, when we ask a question like this, is it likely to rain today? Are you likely to go to Islamabad tomorrow? What are the chances of passing in the intermediate examination? What are the chances of drawing a diamond card from a deck of 52 playing cards? Can we trust the opinion polls of newspapers during election days? What are the chances of getting head on upper side of the coin? All these statements and thousands like them indicate some sort of uncertainty. The probability theory helps us in measuring numerically such sort of uncertainty. Probability is measurement of uncertainty in quantitative terms which prevail behind the occurrence or non-occurrence of an event or combination of events. Learning objectives of this chapter are: after studying this chapter, students will be able to understand the basic concepts of probability, random experiment, sample space, sample points, events, and types of events. Students will be able to use techniques of finding number of sampling points to explain the simple meaning of probability, and students will be able to define and elaborate the term probability. Introduction of probability. Probability is a branch of mathematics concerned with the study of randomness and uncertainty. The 17th century records the first use of probability theory. In the early days, probability was associated with games of chance or gambling. Originally, it was known as science of gamblers because its foundations was laid by two French mathematicians, Pascal and Fermat, in connection with gambling problems. But nowadays, probability theory has wider applications in almost all areas of learning. It is a base for inferential statistics. In everyday life, we face two situations. Either we may be sure about the occurrence of an event or not sure. We are uncertain about the event. If sure, then there is no need of probability. But if not sure, then probability is used. Probability is defined as the numerical evaluation of occurrence of an event. It is a measure of how often a particular event will happen if something is done repeatedly. If an event is certain to happen, then its probability is 1. If an event is not certain to happen, then its probability is 0. So the probability is always lies between 0 and 1. What is probability? Probability or chance is how likely something is to happen. If something has a low probability, it is unlikely to happen. And if something has a high probability, it is likely to happen. Probability is A numerical statement about the likelihood that an event will occur. Meaning of probability. The word probability has two basic meanings: a quantitative measure of uncertainty and a measure of degree of belief in particular statement or problem. Some basic concepts associated with the probability theory are random experiment, sample space, events, simple and compound events, mutually exclusive events, independent and dependent events, equally likely events, exhaustive events, the certain or sure event, the impossible event. Experiment. Experiment is defined as any planned activity to observe some results, or a well-defined situation or process to observe some hidden facts relating to it. A single performance of an experiment is known as trial, and a set of trials is called an experiment. An experiment can further be categorized as random or non-random experiment. Non-random experiment produces identical outcomes or results when it is repeated under identical conditions, whereas non-random experiment is also termed as scientific experiment. Scientific experiments always have a unique results, unique outcomes. Random experiment. A random experiment produces different outcomes or results when it is repeated under identical conditions. That is, an experiment whose results cannot be predicted in advance. Example: toss of a coin, roll of a die, selecting a bolt and observing for whether it is defective or not, etc. are the examples of random experiment. Characteristics of a random experiment. A random experiment holds the following characteristics. A random experiment can be repeated conceptually or practically any number of times. There must be minimum 2 possible outcomes for every single performance of the experiment. There must be some uncertainty in prediction of next trials. Sample space. A set consisting of all possible outcomes of a random experiment is known as sample space. Sample space is usually denoted by S. The elements of the sample space, that is, the possible outcomes of a random experiment, are known as sampling points. For example, find sample space of the following random experiments. Number 1 is random experiment involved is toss of a coin once. Number of sampling points in the sample space is equal to 2 raised to power n, where n is equal to 1 because there is only one coin. If we toss one coin, then n is equal to 1. 2 power 1 equals 1. The sample space will consist of H and T, head and tail, the two faces of a coin. Similarly, for a random experiment toss of a pair of coins, when 2 coins are tossed or one coin is tossed twice, the same outcomes are obtained. Number of sampling points is equal to 2 raised to power n. In this formula, 2 is for 2 faces of coin, head and tail, and n represents the number of coins or number of tosses. Here n equal to 2, 2 raised to power 2 equals 4. In a tabular form, the tabular method is used to find out the outcomes. In this example, first coin has 2 faces, head and tail, and second coin has also 2 faces, head and tail. H, H, T, then TH and TT. 4 possible outcomes are in a sample space HH, HD, TH and TT. Number 3 random experiment is toss of a coin thrice. When a single coin is tossed 3 times or 3 coins are tossed at a time, the same sample space is formed. Number of sampling points in the sample space is equal to 2 raised to power n. Formula is equal to 2 raised to power 3. Here n is equal to 3. The number of tosses or the number of coins. 2 raised to power 3 equals 8. So there are 8 possible outcomes. Using tree diagram method, first coin has 2 faces, head and tail, or we can say on the first draw there are 2 possible outcomes, head or tail. And if heads come on the first trial, the second trial has also 2 faces, head and tail. And if heads comes on the first trial, heads comes on the second trial, the third chance or third toss has also 2 possible faces, head and tail. So the outcomes may become as HHH, HHT, and if on the first trial, on the first toss, head comes up on the upper face, and on the second trial, tails comes up on the upper face, then there are 2 choices for the third trial, head and tail. So we can write HTH, HTT. Similarly, if in the first trial tails comes up on the upper face, then on the second trial 2 possible outcomes of head and tail. And for the third choice, for third toss of a coin, there are also 2 possible outcomes for each head and tail. The outcomes are in the sample space HHH, HHT, HTH, HTT, THH, THT, TTH and TTT. Sample space will consist of 8 possible outcomes when a coin is tossed thrice. Number 4. Random experiment, toss of a coin 4 times. Number of possible sampling points in the sample space is equal to 2 raised to power n. N is 4, so 2 power 4 equal to 16. First coin has 2 faces, second coin has also 2 faces, third coin has also 2 faces, so we can make the outcomes as H, 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 H. Heads comes on all the 4 trials. H, 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 T. H, H, T, H, 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 T, T. Similarly, H, T, H, 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 T, H, T, H, T, T, H, H, T, T, T. These are 8 outcomes with H on the first coin. Then if tails comes up on the upper face in the first trial, then T, H, 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 T, H, H, T, T, H, T, H, T, H, T, T. Now T, T, H, H, T, T, H, T, 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 H, T, 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 T. The possible 16 outcomes are written in a set known as sample space. Number 5. Random experiment involved is a die is rolled. When a fair cubical die is rolled, there are 6 possible outcomes. Number of sampling points in the sample space is equal to 6 power n. Now the formula is 6 power n. 6 denotes the 6 faces of a die. N means number 5 random experiment involved is a die is rolled. When a single cubical pair die is rolled, there are 6 possible outcomes. 6 raised to power n is used when counting the number of sampling points in a sample space. For one die n equal to 1, 6 raised to power 1 equals 6. The sample space will consist of 1 dot, 2 dots, 3 dots, 4 dots, 5 dots or 6 dots. Number 6. Random experiment. A pair of dice is rolled. When a pair of dice is rolled or one dice is rolled twice, the same outcomes are obtained. Number of sampling points in the sample space equal to 6 power n. Formula for finding the number of outcomes is equal to 6 power 2. N is equal to 2 as a pair of dice is rolled. So 6 power 2 equal to 36. Possible outcomes using a tabular method in a two-way table. First die has 6 possible outcomes 1, 2, 3, 4, 5, 6. Similarly, the second die has also 6 possible outcomes 1, 2 dots, 3 dots, 4, 5 and 6 dots. 1, 1, then 1, 2, 1, 3, 1, 4, 1 and 5, 1 and 6. Similarly, if 2 dots on the first die, then 2, 1, 2, 2, 2, 3, 2, 4, 2, 5 and 2, 6. 3, 1, 3, 2, 3, 3, 3, 4, 3, 5 and 3, 6. Similarly, with 4 dots on the first die and 1 dot on the second die for one outcome. 4, 2 is an outcome where 4 denotes the outcome of first die and 2 denotes the outcome of second die. 4, 3, 4, 4, 4, 5, 4, 6. Similarly, 5, 1, 5, 2, 5, 3, 5, 4, 5, 5 and 5, 6. And 6, 1, 6, 2, 6, 3, 6, 4, 6, 5 and 6, 6. There are 36 possible outcomes in the sample space. Sample space will consist of 36 possible outcomes. Events and its types. Event is any desired subset of a sample space. For example, in the random experiment of tossing of a coin once, number of sampling points is 2 raised to power n, which is 2. Sample space will consist of the two outcomes head and tail. Now possible subsets. In order to find the power of a set, we use the formula 2 raised to power n. Here we use 2 power n, 2 is for two faces of a coin. But for possible subsets, in general we use 2 raised to power n. So 2 raised to power n is equal to 2 power 2. Here n denotes the number of sampling points in a sample space. Since there are two outcomes h and t, so n equal to 2. 2 power 2 equals 4. The 4 possible subsets are, we start with an empty set which is known as impossible event. A set consisting of h, a single outcome, so it is known as simple event. Similarly, a set consisting of a single outcome t, it is also known as simple event as it contains a single outcome. H and T, a set consisting of head and tail, it is a sure event or a certain event and is also known as a compound event because it contains more than one outcome. Simple and compound events. Simple event is one which has exactly one sample point. A simple event is also called an elementary event. For example, event A equal to 5, a single outcome when a die is rolled, is a simple event. whereas a compound event is one which contains more than one outcome. For example, event B is equal to 1, 3 and 5 and event C equal to 2 and 4. These are the compound events in rolling of a die. Mutually exclusive events. Two events A and B defined in the same sample space are mutually exclusive if they cannot occur together. That is, if A and B belongs to S and A intersection B is equal to an empty set, then A and B are mutually exclusive events. For example, if we toss a coin, head and tail cannot occur together, so they are mutually exclusive events. Similarly, success and failure are two mutually exclusive events. Life and death, male and female births, a number chosen at random to be even and odd at the same time are mutually exclusive events. Not mutually exclusive events. Two events A and B defined in the same sample space are not mutually exclusive if they can occur together. For example, if set A and set B belongs to S and A intersection B is not an empty set, then A and B are not mutually exclusive events. Example, suppose a card is drawn from a pack of 52 playing cards. It may be at the same time an ace card and a diamond card. Therefore, the events that the drawn card is an ace and a diamond card are two not mutually exclusive events because they together can be occur an ace and a diamond. So they are not mutually exclusive events. Exhaustive events. Two or more than two events are defined in same sample space are said to be collectively exhaustive if their union generates the whole sample space. For example, an event and its complementary event are always performed as collectively exhaustive events. That is, A union A complement equal to S. Another example is, let S equal to head and tail, let A equal to H and B equal to T when a coin is tossed once. Then A union B is equal to H and T and A intersection B is equal to phi, an empty set. Here A and B are mutually exclusive and collectively exhaustive events as they together form the entire sample space. Another example of exhaustive events. Random experiment is a pair of coins is tossed. Then sample space will consist of 4 outcomes HH, HT, TH and TT. Let A equal to HH, B equal to HT and TH and set C equal to TT. Phi is an empty set. Then A union B equal to set A has HH outcome and set B has 2 outcomes. So A union B equal to HH, HT and TH, which is not equal to the entire sample space. Hence A and B are not collectively exhaustive events. Also B union C equal to B set has 2 outcomes and C set has tail and tail. So B union C equal to HT and TH and TT, which is also not equal to entire sample space. Hence B and C are again not mutually exclusive events. B union C is equal to HT, TH, TT, which is not equal to sample space. Hence B and C are again not collectively exhaustive events. They are mutually exclusive B and C, but they are not collectively exhaustive events. Now A union B set union C. A union B union C is equal to HH, HT, TH, TT, which is equal to the sample space S. Hence, A, B, C are collectively exhaustive events. Similarly, sure event S union phi set is equal to S. Hence, S and empty set are collectively exhaustive events. Equally likely events. Two events defined in the sample space are said to be equally likely events if one is as likely to occur as the other. For example, in the experiment of tossing a coin, the event head will appear and event tail will appear are two equally likely events. In rolling a fair cubical die, all the 6 faces are equally likely events because each face has equal chance of occurrence. Independent and dependent events. Two events are said to be independent events if the occurrence or non-occurrence of an event does not affect the probability of occurrence of any other event. Or, two events A and B defined in two separate non-overlapping sample spaces are independent events if A intersection B is an empty set. Dependent events. If the occurrence or non-occurrence of an event affects the probability of occurrence of any other event, that is, events which are not independent are known as dependent events. Two events A and B defined in two separate non-overlapping sample spaces are dependent events if A intersection B is not equal to phi set, an empty set. An example of independent and dependent events. Two events of getting head in the first toss and tail in the second toss when a fair coin is tossed twice are two independent events. An example, the drawing of a diamond card in first draw and the ace card in the second draw when two cards are drawn in succession and the first drawn card is replaced into the pack of 52 playing cards before the next draw, that is, sampling with replacement, then the events a diamond card in the first draw and an ace card in the second draw will be two independent events. However, if the first drawn card is not replaced into the pack before the next draw, then the two events a diamond card and an ace card are dependent events. In this case, sampling is done without replacement. Probability of an event. If the sample space S of an experiment consists of finitely many outcomes or points that are equally likely, then the probability P of A of an event A is equal to probability of A is equal to number of outcomes or sampling points in A divided by number of outcomes or sampling points in S. The language of probability. The terms used in the probability theory are certain, very likely, even chance, not likely, impossible. For a certain event, probability is 1. For example, the sun rising tomorrow. The sun rises every day, so the sun rising is a sure event. Its probability is 1. Similarly, even chance 1 by 2, probability is 1 by 2 of getting tails when you toss a coin. There are two possible outcomes, heads and tails, and 50-50 chances are there for head and tail. 1 out of 2 chances for tails and 1 out of 2 chances for heads. Not likely. When rolling a die, 6 on a dice. Rolling a 6 on a dice. 6 comes up On the upper face of a die, the probability is 1 out of 6. An impossible event has probability 0. For example, if we roll a die, in rolling a single die, the maximum outcome is 6. So rolling an 8 on a single dice is an impossible event, so the probability is 0. Probability scale. These are some statements. Number 1 is the sun will rise tomorrow. The sun will rise tomorrow is a certain event. It's a certain event because the sun rises every day, so tomorrow will also sunrise. This is a certain event. Number 2 is you will live to be 500. Living for 500 years is an impossible event. So, life of 500 years is an impossible event. Number 3. You spin a coin and get a head. This is a likely event and it has an even chance of occurrence of an event because there are two outcomes, head and tail. The chances for heads are 1 by 2 and chances for tail are also 1 by 2. So spinning of a coin and getting a head is even chance. Number 4 is you will see a bus on your way home. That is possible. Sometimes it happens that you see a bus on your way to home, so it is a likely event. Number 5 is you will see an ambulance on your way home. That is unlikely to occur. You sometimes see an ambulance on your way home, but not on every day. How to express probability? Probabilities are most common shown as fractions, as decimals, as percentages. For example, the probability of getting tails when you toss a coin is a 1 in 2 chance or 1 by 2. Similarly, the probability of getting a 3 when you roll a dice in a 1 in 6 chance are 1 by 6. In fraction, the probability of getting tails is 1 by 2 and getting a 3 dots when we roll a fair die is 1 by 6 because 3 is only once out of 6 possible outcomes. So 1 by 6 is the probability of getting a 3 in a fraction form. Probabilities can also be shown as decimals or percentages. For example, the probability of getting tails when you toss a coin is 1 in 2 chance or 1 by 2 or 0.5 or we can say 50%, an even chance. Similarly, a probability of 3 by 4 can also be shown as 0.75 or 75%. How to work out probability? The steps involved in computing a probability are: number 1, question is work out the probability of throwing an even number on a dice. When we throw a dice, which is a fair die, there are 6 possible outcomes: 1, 2, 3, 4, 5 and 6. So first step is count up the total number of possible results. When throwing a dice, for example, there are 6 possible numbers the dice can land on: 1 dot, 2 dots, 3 dots, 4 dots, 5 dots and 6 dots. And we are interested in even dots. In the second step, count up the number of results you are interested in. In this example, you are only interested in throwing 2, 4 or 6, all the even numbers on the dice. So you are interested in 3 numbers. Count the favorable outcomes. so the favorable outcomes are 3. Total possible outcomes are 6. We count the total possible outcomes in the first step. In the second step, we count the number of favorable outcomes, and in the third place, the probability of getting an even number on a dice is 3 chances out of 6 chances. We use the formula of probability. Probability of an even number A is equal to favorable cases divided by total cases, that is 3 by 6. Can you tell me what the probability is as a fraction? Question is, what is the probability of rolling a 4 with a dice? When a dice is thrown or when a dice is rolled, there are 6 possible outcomes. 4 is one of the 6 outcomes when a die is rolled. So the probability is 1 out of 6. Similarly, what is the probability of rolling an odd number with a dice? When we roll a die, there are 6 possible outcomes: 1 dart, 2 darts, 3 darts, 4 darts, 5 darts and 6 darts. Among 6 possible outcomes, there are 3 odd numbers: 1, 3 and 5. So the probability of rolling an odd number with a dice is 3 out of 6. Another question is, a bag contains 7 buttons. 3 of them are green. What is the probability of picking a green button from the bag? There are total 7 buttons. 3 are green and the remaining 4 are not green. So the probability of picking a green button, there are 3 favorable outcomes for green button. So 3 out of 7 is the probability of picking a green button from a bag containing 7 buttons. A bag contains 3 red and 5 green marbles. What is the probability of picking a red ball? A bag contains 3 red and 5 green marbles. What is the probability of picking a red ball? Since there are total 8 balls, so probability of getting a red marble, so the probability of getting a red marble is 3 out of 8. Some useful information is given over here. 52 playing cards in a deck consists of 4 suits. Each suit has 13 cards. The 4 suits are clubs, spades, diamonds and hearts. Clubs and diamonds are of black color and diamonds and hearts are of red color. 13 cards in each suit consist of ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, the numbered cards, whereas jack, king and queen are the face cards. So spades are 13, hearts are 13, similarly diamonds are 13 cards, so clubs are 13. 3, 3, 3, 3, 4 threes are 12 face cards are there in a pack of 52 playing cards. Similarly, a regular dice has the numbers 1, 2, 3, 4, 5 and 6. For practical purposes, an extension activity is take a coin and toss it for 30 times. Every time the coin lands on, you are going to record whether you get a head or a tail and write H for head and T for tail in each of these boxes. Then count how many heads are there and how many tails are there. This is an activity for the practical. Second activity is you are going to roll a dice a total of 30 times. Every time you roll, you are going to record the score on the dice. Write the score you get each time in the table. 6 possible outcomes are there when you roll a dice. Write the outcomes in these boxes and then count the number of 1s out of 30, the number of 2s out of 30, the number of 3s, number of 4 darts, number of 5 darts, and number of 6 darts. Thank you. Have a nice day.